So in the example number 6, we will have to find radius and interval of convergence for the following series. Sum going from 0 to infinity, minus 3 to the k times x to the k divided by square root of k plus 1. According to the plan of actions here, we will first apply ratio test to find out what r is. Okay, so the ratio test, we will look at the usual limit, and here ak plus 1 is minus 3 to the k plus 1 times x to the k plus 1 divided by square root of k plus 1 plus 1. This entire thing will be divided by ak, which is simply minus 3 to the k times x to the k over the square root of k plus 1. As a reminder, this is the expression for ak plus 1, and this is the expression for ak. The kth and the k plus first term of this series respectively. We can drop the minus 1 again. So observe that minus 3 to a power is the same as minus 1 to that power times 3 power. So this is an alternating form of minus 3 to the k. This is how you can think of it. And since minus 1 has the magnitude 1, we can drop it right away. So this becomes the following limit: 3 to the k plus 1 times x to the k plus 1 divided by square root of k plus 2, and then multiplied by, I'm going to flip the second quotient, square root of k plus 1 over 3 to the k times x to the k. And cancellation. What will cancel? Well, the powers of x, the powers of 3, and that seems to be it. So I will have the limit, k goes to infinity, 3x divided by square root of k plus 2 multiplied by square root of k plus 1. Let us use again that the square roots, both square roots, are positive, so there is no need to keep them under the absolute value, and this limit is simply absolute value of 3x. This is the only part that can become negative, multiplied by square root of k plus 1 over the square root of k plus 2. And as we already did a couple of times, observe that 3x is independent of k. It is therefore just a constant in terms of this limit. So we are looking at the absolute value of 3x multiplied by the limit. And then it is straightforward to compute that value of this limit, which you can rewrite This here is just square root of k. Whoops, this was 2. This is the square root of k plus 1 over k plus 2, and this goes to 1. Therefore, the answer, the output of the ratio test, we have absolute value 3x here. The output of the ratio test being dependent on x means that we must now solve the absolute value of 3x less than 1 to determine what r is. If you look back at the theorem, you see that the form of the interval of convergence is the one of this inequality, right? So the condition for the interval of convergence is absolute value x minus a less than r. In our case, a is simply 0. We do not have anything x minus anything like x minus a number here, so this means that a is 0. And so the output of the ratio test, this one here, is less than 1 if and only if absolute value x is less than 1/3. So what we did was dividing both sides by 3. Now let us compare this inequality to the general form of the inequality we have for the interval of convergence. This is the general form. This is what we have. If you like, you can rewrite this as x minus 0 is less than 1/3. And then comparing these two, you will conclude that r, the radius of convergence in this case, is 1/3. Great. It remains to determine the behavior of the series at the endpoints of the convergence interval. So we know what the convergence interval looks like. We have the number 0 somewhere here, and then we have the interval of radius 1/3 around it. But we do not know anything about the endpoints. What is the behavior of our series at the endpoints? So to find out, let us look at the values of our series at the endpoints. So here's what we have. At the end points here and here, let us start with 1/3, say. When x equals 1/3, our series which has this form becomes so you will have sum k from 0 to infinity minus 3 to the k, but remember, minus 3 to the k is nothing but minus 1 to the k times 3 to the k, and it will be multiplied with 1/3 to the k. Right? Since x is 1/3, we have 1/3 to the k here. And everything divided by square root of k plus 1. Great. Now what happens is we have cancellation right here. And the output of our power series at the right endpoint ends up being minus 1 to the k times 1 over square root of k plus 1. And this series is So I encourage you to pause the video at this point and think about what you can say about this series. This is, of course, an alternating series, and it is convergent by the alternating series test. Great. That's what we know about the right endpoint. We know that our series converges at the right endpoint. So let's include this interval into this point into the interval of convergence, and consider the left endpoint, x equals minus 1/3. For this value, the series, which had the form we wrote over here, will be the following. So we'll have, first let us again rewrite minus 3 to the k as minus 1 to the k times 3 to the k. And we will replace x with minus 1/3. Similarly, minus 1/3 is minus 1/3 to the k is minus 1 to the k times 1/3 k. Everything divided by square root of k plus 1. Cancellation. Great. These two together, by the way, are equal to minus 1 squared to the k, and that is simply 1. So all in all, our series becomes the sum of 1 over square root of k plus 1. Now this series is, and again, you should pause the video and think what you can say about this series. So now you know the answer. This is a divergent series, and what seems to me to be the easiest way to check this is limit comparison test. So it is divergent by the limit comparison test and so the series it should be compared to is the sum of 1 over squared k. So the sum of 1 over squared k is, of course, divergent as a p-series. And so therefore, by the limit comparison test, they both of these series must be divergent. And so the left endpoint here must indeed be excluded from the interval of convergence. And so the interval of convergence for this series has the form of the half-open interval minus 1/3 1/3, and radius of convergence is, of course, 1/3 as well. So this completes the answer to this question.